Welcome everyone to this online lecture. My name is Merel Posma. I am one of the editors at Utrecht University, and this next to me is geophysicist Rob Govers. We're going to talk about today is earthquakes and the science behind earthquakes. Why did this earthquake specifically happen in Turkey? What happens during an earthquake, and what do scientists do after an earthquake? After his lecture, which will take about 30 minutes, he will answer questions. So please ask your questions in the live chat, and then we will get to those. Rob?
Thank you very much, Merel. So my name is Rob Govers, and I will talk about specifically the February 6, 2023 Turkey earthquakes. Before I start, we should all remember that this is a truly sad event with all the victims, and obviously also people who lost their homes, all the wounded. And although I'm going to start with a rather technical story, talking about the knowledge that we have about these events, it's something to keep in mind clearly, but it will not clearly also be the focus of what I will be saying. I will focus, because that's my background, on the Earth and Earth sciences. And the Earth sciences are interesting because obviously they are the cause of all the things that we see here. Deformed roads, deformed railroad tracks, and actually the entire landscape has been transformed. Now, why is Turkey such a seismically active area? And the reason for that, the answer to that, is essentially plate tectonics. The plates involved here are the Nubian plate, as you can see here at the lower end. That is the plate that is to a large extent part of Africa. There is in the north there is the big Eurasian plate, and those are the two main players in this region. Africa is moving to the north at a rate of roughly a centimeter per year, a couple of 10 millimeters per year. And there's another player here, a smaller plate, and that is the Arabian plate, which also is moving to the north at a higher rate on the order of 2 centimeters per year. Now, in this entire crush zone, there is the Aegean, and that is largely, that's part of Greece, Anatolian, and that's Turkey, deformation zone. And it's due to essentially the crush, the compression between those plates that all this happens. And you can see here in the figure, all those balls represent epicenters of earthquakes that have happened in the past. And although we will focus here on the central or eastern region, you will realize that there's much more areas here that also exhibit major earthquakes in the past. Now, these days, scientists are able to measure the motions of the plates, and although they are moving very slowly, it is possible to do so with GPS instruments. And likely you are familiar with GPS instruments, but different from the type of apparatus that we have here for doing these measurements. Within your cell phone, your location is determined using GPS satellites, which sit there at an altitude of roughly 20,000 kilometers. And I'd like you to keep that number a little bit in mind, because when we start looking at the velocities of the plates in this region, and here you can see a summary of those velocities. These are the velocities relative to the Eurasian plate there in the north. We see that the velocities, the arrows, the length is on the order of a few centimeters here, 2 centimeters, and then increasing to 2, 3, and in some locations 4 centimeters per year. I myself find that magic, there's this network of satellites which sit there at this high altitude, and we are able with this precise instrumentation to measure the ground deformation with a precision of a couple of millimeters per year. Okay, how often are there large earthquakes within Turkey? Turkey has a long record of major earthquakes, and since the year 1900, we have records of more precisely located earthquakes because of better observation networks of seismometers. And here you can see on the lower graph, you can see that this is time. It starts in the year 1900, and this is where we are now. In the vertical axis, there's magnitude, and you see that a very big ball indicates here a large magnitude earthquake, which happened in the year 1939. And that ball here in the geography sits here along a major fault that we will get to learn a little bit better, and that's the North Anatolian Fault. The other thing that you see is that the majority of the time, the big earthquakes in this geographic window are on the order of 7, maybe a little bit less, a little bit more. But these earthquakes stood out as sitting closer to magnitude 8. And then the most recent earthquakes that happened along this fault, we'll talk about that shortly, they are of the same exceptional magnitude. As you may remember or know, is that the biggest of the two was a 7.8. And that happened very close to the city of Gaziantep. Okay, there's more information available about the situation before the earthquakes. Geological field mapping and historical records, historical accounts, I should say, of the events here in this region show something very clearly. Namely, there in the east, there is this East Anatolian Fault Zone, which essentially is oriented towards the Mediterranean Sea. And you see that there's these barbed lines representing the former historical geological collision between the Arabian Plate and Anatolia. A very important fault here, besides the East Anatolian Fault Zone, is this Surgu Fault. And that is one of the major faults which is recognized in the field. When people, geologists, go do field work, they see that fault in the landscape and are able to do measurements on those faults. And indicated here by the balls are earthquakes that happened in the 16th century, the 20th century. And so this fault was known to be capable of very significant earthquakes. Indicated here in the ellipse is a region where the fault trace, that is the fault at the surface as it can be recognized by geologists, is incomplete. It's not a complete through-going line like other faults that I talked about. The other thing that is noticeable is that in this region there have been no records of major earthquakes during at least the last 200 years, but perhaps maybe longer. That's something that will hopefully with further research will become clear. And this region will show to be very interesting and important for the earthquakes. So what happened during the earthquakes last week? Well, I already indicated there were 2 major earthquakes. Let's a little bit fast. The first earthquake here was the biggest earthquake. It had a magnitude of 7.8, and that is on a scale that is totally unimaginable, the amount of vibration that it causes, certainly if it is located so close to the surface. The earthquake itself was followed by a large amount of aftershocks. That's mostly these purple circles. And aftershocks, they're defined as smaller events, significantly smaller events that happen after the main shock. And what typically is the situation is that the the epicenter of the main shock is just a point, but then the aftershocks, they illuminate what part of the fault really slipped during the earthquake. Now, probably you have been already staring at this magical beach ball, and indeed earthquake seismologists call it a beach ball, but it is actually a little bit more informative than just a beach ball. What it informs seismologists about is the type of faulting that happened during this earthquake. Now, why is this necessary? It has to do with the nature of the Earth and the fact that we live on it. Most earthquakes happen within the planet, and they are therefore not accessible to geologists, for instance, for direct observation, where you can hammer the rock, you can investigate the rock, things like that. No, most earthquakes, we have to use seismological observations to deduce what really happened there deeper in the earth where we cannot reach. Now, this beach ball, however, for the people who have a little bit of training in this, does mean something, and you already saw it briefly. What it means is that before the earthquake, and at the very top over there, you see there was essentially nothing was happening. There's a nice house which has been built there, but the plates are moving relative to another. And with time, now I'm referring to the middle figure, after 200 or longer years, the blocks of rock have moved relative to another, and that motion can be quite substantial. In this case, we estimate it must have been on the order of 3, maybe 4 or 5 meters even. Well, all this deformation there that you see in the bending of that plate is representing something that we know is happening, namely that the rocks are bent and they store elastic energy, and that's all is possible because the fault between the two blocks here, this fault, is locked. It cannot move. It is frictionally glued together. But the forces increase and increase, and at some point it slips. And that's indicated in the lower figure here. And what you can see is the block from the perspective of the person in the house. Luckily the house survived. From the perspective of the person in the house, the block moves to the left. And if you were to stand on the other block, you would also see this block move to the left. And that's why we refer to this as a left slipping fault. Not that is not itself very important. It does, however, fit in the overall picture of plate tectonics that we understand for this region. Okay, that was for the first fault. The main earthquake, the M77.8, happened middle of the night, with the consequence that many people were at home and became casualties during the event. The second earthquake happened in the afternoon, and that was in magnitude 7.6, so very close in magnitude to the first earthquake. It also happened on the other fault, and that's why we consider this a second earthquake, not simply an aftershock, both because of its relatively similar magnitude and because it happened on a different fault. That earthquake, the second earthquake, generated its own aftershocks that you can see here in the light purple bulbs, and that those are still going on. The nature of the fault slip, you will recognize that the balls have a similar sort of a shape. They are not identical. When you look in detail at the second earthquake, the magnitude 7.6, it has interesting information that I'll come back to later when we talk about INSAR, the radar images. Okay, but in essence, the two blocks both had left lateral, so left slipping motion during the earthquake, and both were very substantial. Okay. I'm now going to show a similar sort of animation where you can see the first earthquake and the aftershock, and then the second earthquake and the aftershocks. And you see what I mean, that each of the earthquakes had their own relaxation and aftershock behavior. The other thing that you can see on the vertical axis, there's the magnitude. What you can see is there's a very substantial amount of fairly big earthquakes. And actually, I didn't play this all the way until yesterday, but they continue. And that's an aspect of big earthquakes that is disturbing and that is really important. Namely, the earthquake activity does not stop here with a major earthquake. It just continues at a lower level, but because the major earthquake was so big, the aftershocks are also very big still and capable of causing significant damages. Okay, the length of the faults we estimate from the aftershocks for the first event. This is I call it the East Anatolian Fault. Maybe with further research we will give this segment a different name, but for now I'll call it like that. This entire length is about 300 kilometers. And the second fault, the Surgu fault, is about 300 kilometers in activated length. So 2 major earthquakes on 2 faults. Using seismological observations, and this is really high-end stuff, we are able to image the amount of slip on the faults. And here you can see the fault as if it has been lifted out of the ground, and we can now examine it. And here, this is when we look onto the fault, you see the colors indicate the amount of slip that has occurred relative to the other block, and you can also see the direction that it indeed is roughly horizontal. Now, the darkest region here is above 3 meters in slip. The numbers here indicate time, and the epicenter, or I should call this the hypocenter because it's at depth, the hypocenter is where the earthquake starts. It's not a very important part of the earthquake sequence. It's just where the earthquake starts, and you can see that there is very little slip there. Actually, with time, this is 10 seconds, this is 20 seconds. After roughly 20 seconds after the earthquake had started, the slip became really significant. And mind you, this was also very close to the surface, so close to population centers. Slip is the most important cause of energy release, and so that energy here was transferred in the vibrations, the seismic waves, which then resulted in the shaking of the ground. Okay, now the overall earthquake lasted on the order of 100 seconds. And that is quite normal for such a large event. But it is, again, disturbing that this heavy shaking lasts for nearly 2 minutes, as you can imagine. The second earthquake had looked completely different, as you can see. The slip was concentrated much more around the epicenter. There the epicenter was this same location where also the largest energy release occurred. And now it looks like also the slip was much more concentrated. There was much more slip that happened on this fault. It sat, however, deeper. than that of the first earthquake. So that was also a relevant difference. Okay, because it was a little bit shorter. Because it was lower magnitude, the event itself also lasted a little bit shorter, but not very much. Okay, now these days earth scientists have various tools to look at events like this, and the high precision ESA Copernicus Sentinel satellites are capable of using radar images to measure the deformation of the ground. They're fairly complicated figures, but first let me talk about the principle. This shows essentially two satellites or one satellite at different locations, and with radar you can measure the distance to the ground, and when you do that twice you can subtract them or do an interferometer. You can find the difference between those radar images, so you can see where the ground is then deforming. Now, there's a lot happening in this figure, and part of the reason for that is that the time between those two passings of the satellite is substantial. Remember, the earthquakes happened on February 6th. So what we see here on the Sugu fault is all the deformation that happened, in this case in east-west direction, of the main quake along that fault, but also of all the aftershocks. So, and the way you can recognize the deformation is because you can see a color difference. This is motion to the left, so westward, and here is motion to the right, eastward. I'm staying with the Sugu fault when we're looking at the the north-south component, because you also can see some color differences here between the north and the south, which seem to suggest that there may have been also a little bit of underthrusting, and that was the complexity I was talking about earlier when I talked about the beach balls. That would certainly fit in the overall pattern that the geology presents, but something to follow up. The main shock had an imprint in the east-west, as you can see, displacement, but the main imprint is visible here in the north-south component. Here, stark differences in colors. Now, you might say, well, yeah, but I see lots of stuff happening here, and that's true, because the radar is sensitive not just to earthquakes, but all sorts of changes, for instance, snow cover, water, and those kind of things. So it's particularly difficult to interpret the entire picture. Okay, was it a coincidence that there were two earthquakes? And I'm going to try and convince you that it was not. When we calculate the stresses due to the first earthquake, the magnitude 7.8, what you see is that the stresses are negative, a negative change, which means that essentially the hazard has decreased, has dropped. But you can see ahead of the fault here and there, the stresses have increased. And interestingly, aftershocks directly following the main shock nicely fall within this region, here and some here. But you'll also notice that there's other aftershocks that are located here. And they have a different reason that I'm not going to talk about, but this is not a problem, let's say. The thing that I'd like to talk about now is this. Here you can see the Sugu fault, where a fairly moderate, but it is an increase of stresses occurred due to the main shock. So our thinking right now is that this stress change by the 7.8 increased at least the probability of the 7.6. But whether it caused the earthquake, that remains to be seen. Were these earthquakes expected? The earthquakes were expected first of all, because my colleagues, Rob Reilinger and McCluskey from MIT, started doing GPS measurements in, late the previous century. And here you can see the results of that. And particularly here in this region, they noticed that there is a velocity contrast between essentially this region and this region, Arabia and Anatolia. And they already at that point said that this pattern that it follows is indicative of elevation of deformation, and that is built up towards an earthquake in this region. There have been many studies after that with similar techniques, but other data that have confirmed them. The latest that I found is from my Turkish colleagues who also found a similar sort of step. The figure is slightly different, but it has the same conclusion, namely that the rate at which deformation is building up in the area is on the order of 1 centimeter per year, maybe slightly less. So yes, from this perspective, from the measurements, it has been clear for decades that something should be expected in terms of earthquakes. The researchers from around the world, let me emphasize that, were concluding that earthquakes were coming. Another most recent type of observation is again based on these radar images. And here you can see results, very nice results from the Leeds group, where they mapped terrain accumulation from this radar. Now, I should start with the thing which immediately jumps to the eye, which is the North Anatolian Fault, this big and particularly fast-moving fault in the north, which is particularly relevant for Turkey at large, and particularly Istanbul here in the area. But what you can see here is on the slower East Anatolian Fault here, there's also colors indicating it's not white, there is accumulation of strain. And essentially these observations, they confirm what was already concluded also from the GPS measurements, meaning we're building up towards an earthquake here likely. Now, this work, as you can see, was done in 2020, and it is therefore, was pertinent for the region. Okay, we're moving from earthquakes. We move to the effects, and that's going to be the last part of my presentation. Where is it safe? Now, there's two things that I'd like to separate very clearly. When you have at the horizontal, before we go first to the graph, at the horizontal axis there's distance, a logarithmic scale, and on the vertical axis there is the so-called modified Mercalli scale. The name is not particularly important. Essentially, call it the shaking intensity. And the shaking intensity is what you'd like to know if you're sitting in a building or a house, obviously. So this scale is particularly relevant. Now, you can have a magnitude 8, and if you're sitting at the fault, you'll have a shaking intensity on the order of 10. Which refers to, here you can see the perceptive scale. You will probably be in a region then where extensive damages are occurring. It may have been that within the magnitude 7.8 area that the shaking came at the level of 9, perhaps. We'll talk about that shortly in a little bit more. But what's also clear is when you go away, essentially the line drops very rapidly. So meaning that at 100 kilometers away from the fault, with that same moment magnitude, the shaking is much less. And I don't think anyone is surprised. The energy distributes over a much wider area, and as a consequence, the shaking decreases. We have this experience ourselves. The what is important, obviously, is that you will have a different line for magnitude 8 than for magnitude 6 and magnitude 4, meaning for a magnitude 4 in most areas, yeah, it will be felt, as we can see, but it will not result in damages, which is different for magnitude 6 and magnitude 8. So distance matters. Distance helps, and not living close to a fault which is capable of these types of magnitudes is relevant. Okay. This was the shaking intensity that was determined from calculations for the 7.8 region. And you see that here the colors are fairly intense red, so close to 8, 9. And once you get above the oranges, so 7, that's roughly a threshold value when in many countries there will be damages. Then, yeah, essentially you will there will be accidents as a consequence. If there is something that we can compare it to, these types of numbers, because here you can see there is the peak ground acceleration. And what that says is that for a, let's stay here at the upper end, for a magnitude 10 plus, it means that the accelerations can be so fast that really a building or something extremely heavy that you can think of is thrown up in the air, becomes weightless for a very short time until it comes down. So that's what the 100% gravity acceleration does for you. Now, even lower accelerations for here, for 9 or here 8, this was most of the area, 40%, is really damaging for housing areas and all sorts of infrastructure that is not or incompletely protected. So why are some earthquakes much more deadly than others? Well, there's a couple of factors. The first factor is easy. If there's no people in the area, there is no problem really to society. This was unfortunately a very densely populated area. Then there is earthquake preparedness of the buildings. That is clear. There is early warning systems, building integrity meters. Not to forget, if there is a warning system, you want your population to know what they need to do with such a warning. And for instance, Japan is an example. There they do have a warning system, and they do train the population such that the people know they have to grab a bottle of water, and they know also that they have on the order of seconds, sometimes 30 seconds, but it is not very much time not to leave an apartment building. But if you know you have to grab your bottle of water and you know that you have to sit behind your bed, for instance, then you stand a better chance of surviving. And not to forget, there is geological conditions which may make the situation much worse. And that's particularly related to the presence of basins, sedimentary basins, or water-saturated soils. Okay, what you see in the graph is that the number of fatalities due to previous events, like Haiti in 2010, Wenchuan 2008, is basically unrelated to magnitude. And that just says all these aspects are more important than the magnitude of the event. Okay, a few points related to those factors. Building quality was, for instance, very clear, a major player in the Haiti event. Here you can also see that the same types of collapses. And there, a large fraction of the buildings that collapsed consisted of brick. And there was also collapses of weak frame, but still the number of casualties here were much higher in the brick buildings than even the buildings with a weak frame. So having some some sort of functioning frame is really important. Another way of looking at the Haiti event and what happened there is like this. Haiti, the magnitude of the event was a 7.0. And in Chile, 1 month after, the magnitude was close to 9. So that's a factor of 500 in the energy that was released in Chile. 500 times as much. However, the number of casualties in Chile was well, I shouldn't say only, but that's way 570 too many. But it doesn't compare whatsoever with the 222,000 plus. That's a factor of 1/430. So the difference is in Chile, people are well prepared and building regulations are upheld very strictly. Okay, then I'd like to say a few things about the subsurface, because the subsurface, it will be shaking, and these are little seismograms, so shaking of the ground of various locations, and they illustrate the role of the subsurface, and the subsurface is important. What I'm showing next is a movie of a hypothetical simulation of an earthquake, which never happened. But in this simulation, what you can see is that the subsurface starts doing its thing. And particularly here, you can see there's these blue waves that stick there, and essentially they're going back and forth within. This is a basin. And basins act to essentially trap waves and keep them vibrating and vibrating. And so those are really damaging for buildings. By the way, it's these simulations that involve quite a bit of geological knowledge that are being used to prepare buildings for essentially for events which have not come to pass. Okay. The other fact is that liquefaction can not only drown cars, like here in Christchurch, but it can even topple buildings. And certainly also in Turkey, there was the risk of liquefaction. The release of the water from the ground destabilizes the ground so that essentially buildings can fall over. It is for a properly trained geologist, it is entirely possible to recognize that there have been previous of these liquefaction events. So in principle, it is possible to warn and to prepare for that. There is a final warning system that I already mentioned, based on the fact that any earthquake generates at the same time, sends out waves which are very fast and small, and big waves. And the big waves are the damaging waves. They are the ones you want to know about. Now, based on these waves, which arrive at seismometers much earlier, sometimes on the order of a minute or so, they can be analyzed and they can be used to send out warning. It's operational in Japan, and it distinguishes small events that are nearby from large events further away. And the good thing about it, it automatically closes down gas, electricity, high-speed trains and trams. And it issues alarms to nuclear power plants, factories and so on. So it's truly a valuable kind of asset. Okay, this was my last slide. And I want to end with where I started, with the victims. And I call for your attention to the victims. It's all scientifically of some interest, but really what matters is the victims. And there will be this how do you call this? I forget what the word is. Money will be collected. People will ask you for money and aid. So please donate to Giro 555. That's it. Thank you.
Okay, Rob, thank you very much for your lecture. I would like to go to some questions that were asked in chat. And if you have any other questions, please ask them. And now is the time that Rob can answer some of them. One of the questions that someone asked is, could you explain what the beach balls represent? Because you kind of went into it a little bit, but can you talk a little bit more about that?
I have to admit that it's a fairly technical thing, and I didn't prepare a figure for it, so you'll have to bear with me and look at my hands. Essentially, when an earthquake happens, there's a radiation pattern. There is compressional waves sent out in one quadrant. There's dilatational waves sent out another quadrant. And actually, it's a axisymmetric pattern, meaning the two dilational quadrants oppose each other and the two compressional quadrants oppose each other. Now, when you have that radiation pattern, so the waves are being sent out, those quadrants can be recognized back in the recordings of the seismometer. In the waves that arrive there. For instance, in the first arriving wave, the fastest wave, either you see the needle go down first, or you first see it go up, if it's properly aligned. So it is something that requires quite a bit of seeing many seismometers all around the world. We have a broad network of seismometers. Maybe that can be shown here behind me. That's the global network of seismometers. And so those help us to constrain that beach ball.
Okay, thank you very much. Someone else asks, if the strain buildup is so much larger along the North Anatolian Fault, would there be a significantly larger earthquake risk there?
The strain buildup is faster in the north, indeed. However, there's more frequently there is earthquakes there. So it seems like that balances out in the sense that along the northern system there have been more 7 plus earthquakes, and like we saw, 1939, a 7.8 like event also. But it seems like both faults, both the east and the north Anatolian system, are capable of similar magnitude faults. It's just a frequency that they happen more often in the north than in the east.
Okay. And then building off from that question, we have a question from someone who lives in Istanbul. They say a large earthquake is predicted to occur here, has been predicted to occur here for many years. Do you have an estimate when this earthquake will occur?
Unfortunately not. And this is the reality of earthquake science right now. We have been looking at many precursors, so things that happen before earthquakes that would help us to predict whether an event comes. But the timing is something that we cannot predict. There's other aspects of earthquakes that we do have a sense about, and specifically that is the magnitude. That's from historical observations typically, from the type of earthquakes, that's from the geological context. But it's a little bit like a weather forecast where you have been told, okay, there will be sun and there will be rain, but it's not very useful because you want to know when the sun and the rain are coming. And that's the aspect that we are not so very good in. However, we are able that in regions where we have many observations, both GPS, seismology, so everything that is possible to make assessments of how long, I should say it like this, if what the risk is, for instance, when you live, for instance, in California, what the risk is that your house experiences this heavy shaking within a 40-year period. Now, and why is that useful? Well, you can decide, I cannot live with that risk and move somewhere else, further away from the fault, that's clear. You can decide to reinforce your house, which is useful, and get an insurance. Because insurance companies obviously are also very interested in this information, what the risks are associated with earthquakes. So it is not completely useful, but it is not the type of information that people who would like to, for instance, not be in such an earthquake zone while it happens, can rely on. So earthquake prediction, in that sense, doesn't exist. We cannot say, go next Monday, go visit your grandmother because there will be an earthquake in your town. That's I'm not even sure that ever is possible.
All right. And you can't predict when an earthquake will be. The same person asks, did the recent earthquakes in the south of Turkey increase the risk for Istanbul? So the same way in that you told about that other fault that kind of got activated. Yeah. Do you think the same thing can happen in Istanbul?
Yeah. I did not look at that specifically as yet. If the director can allow me to show me a figure. This figure, thank you. What I do have a calculation about done by Tembler, as you can see there in the upper right. What they calculated was the stress effect of both earthquakes. I didn't show this yet, but this is both the 7.8 and the 7.6. And you can see here there is a red zone, and here there's a red zone, and those are the zones which would be expected to see earthquakes in the next future. However, what you also see is that here is the North Anatolian Fault, and I think Istanbul is somewhere out there. It's beyond the figure. It's essentially white. It means that the footprint of earthquakes, it is rather regional. It doesn't extend that far out all the way into Istanbul. So I don't expect this earthquake to have a significant effect on the imminent earthquake that indeed should be expected in Istanbul.
Okay, thank you. And I was also wondering, you can do, or you just talked about predicting earthquakes in advance. Right after the earthquake happened, experts were really quick in predicting the casualties and the economical damage. How did they do that so quickly?
Yeah, that's based on a vast amount of information that is being collected by geologists, by the earthquake people. Let's say the seismologists, the tectonophysicists. They all accumulate the type of information that is needed to make such a prediction before an earthquake happens. They put all that in a model, and if then there is an earthquake and there's real information, that information is being used to immediately, there is an earthquake, if all the seismometers go off, and it triggers that. It triggers that model, and such that not only is there the shaking estimates that I showed, but also indeed the economic consequences and estimates of population, because what's part of that model also is information about the quality of building in particular cities, particular countries, and those kind of things.
Okay, thank you. We have time for a few more questions. Someone asks, some experts say that planet positions have an effect on earthquakes. Is this true?
Now, the fair answer is I don't think so. But the best answer is that to explain how we as scientists, how we deal with this. The issue is namely that it is not about opinions, science. It is about facts, and the facts that we essentially use, it's always a pretty standard procedure. We have a record of earthquakes, meaning we know when earthquakes in particular area happened. That happened then, and then. Okay, and then what you can then compare that to is information, for instance, about the planets. When the planets were in some location, and does that mean that there is a significant change in gravity or electromagnetics, for instance, for that specific area? So essentially, you're comparing time series of the earthquakes and the planets in that case, and then it's a matter of saying, I see fairly systematic that there is something planet-related that happens before an earthquake. If that's the case, then we may not necessarily understand it, but that's not a problem. The issue is namely then that the data suggests that you should look into that more carefully. However, the things that have been proposed are people noticed typical behavior of dogs, for instance, or birds or turtles, and particularly in days, centuries ago, when people lived more closely with their animals, they saw a lot of that. And so it was clear that dogs barked before, after, and during earthquakes. But the problem is dogs always bark. So they did also bark if there was no earthquake. And so you have to also be careful to say when there is a prediction and test whether it is a false or true prediction. Now, all this is essentially cross-correlating time series, and we do that carefully, and we thus far have not found anything that is predictive in that sense.
Okay, that's clear. I was wondering, is it true that we no longer use the Richter scale for the magnitude of earthquakes?
Yeah, that is correct. Again, that is not an uncommon question, so I had prepared a little bit of background material there. And what you can see here, this thing actually is much higher than I am. I can hardly reach as high. So that's a gigantic apparatus. That is one of the very old, called the Wood-Anderson seismometer. And what you see here on top, that is a modern seismometer, and it is no higher than this. So it's much more compact, but that's not the issue why we don't use the Richter scale. If the question is, what do seismometers have to do with the Richter scale in the first place? Well, the Richter scale, initially, it was based on measuring the amplitude, the maximum amplitude of the waves that came in at this particular station with this apparatus. Okay, and so you would measure that, and then you would translate that into the magnitude. Now, this, although it's much smaller, it's much more advanced. It is able to pick up completely different waves, including the waves, a much broader spectrum of waves, I should say. So it's more richer in the information. It's much more sensitive and accurate, and so it is something that is certainly superior. Now, you could, in principle, of course rescale the newer data to something that is comparable to this. But there's other reasons why we don't like it. And that is my next slide. Because Richter, that's the name of a scientist who devised his scale. What he did, he located earthquakes by using a triangulation when there was an observation seismometer here, and here. And then he used the distance, because Richter was not stupid. He recognized that sitting at a larger distance, you would have smaller magnitudes of the shaking. And then what he did, he devised this kind of scale for magnitude 4 or magnitude 5. It's similar to the scale that I showed you earlier during the lecture. However, there is geology in this scale. The local conditions make a difference. And so the drawbacks of this scale, I'm not sure that everybody can see, so I'll read it, is all this work was done in California. So it's probably nice and well working for California, but California not only has a different geology, it also has smaller earthquake. And that brings me back to the seismometer, this huge thing, because it was not capable of recording amplitudes larger than a given number. Meaning, essentially, that at the end of the day, it was not able to record earthquakes bigger than 7.5 or so. And so it does not work for the rest of the world, therefore. And that's why a new scale was devised, which does not have these problems, and which from a physics perspective also is more better, because it no longer works with the earthquake shaking, but which is the energy recorded at the seismometer, but it does a projection such that it makes an estimate of the energy that is released at the source. So we really try to estimate with the moment magnitude scale what that energy is. Now, a last thing about the Richter scale. The Richter scale is cleverly reproduced by the moment magnitude. The way the moment magnitude is calculated is a two-step approach. You first take the rock elasticity, that's a big number, the area that ruptured, and I showed that in my talk, and then the amount of slip that occurred. You multiply them simply, and you have your amount of energy. And what comes out is a gigantic number. That's truly impressive, the amount of energy that's being released. The biggest earthquakes release the amount of energy that a small country like the Netherlands uses in 1 year, for instance. Okay, but because it's a big number, a log is taken of that number, and here comes the Richter scale, because this subtraction of 9.05 and then division by 1.5, the whole point of that is to make the number of the moment magnitude come out the same as in the Richter scale, which was already well known in the 70s when the moment magnitude was proposed. So for the range of 4 to 7 plus, the numbers are the same. But beyond the 7 plus, the Richter scale could not produce magnitudes for instance, the magnitude 9s that we saw in Japan, in Tohoku, the Fukushima earthquake. And even probably the 7.8 in Turkey this week would have been a stretch. Long answer, I hope it's clear.
Thank you very much. I thought it was a simple question, but apparently not. We're out of time for the questions. Thank you very much, Rob, for your time and for doing this. Thank you for everyone who is watching and sent in their questions. If you missed any of this lecture, after we close this live stream today, we're going to keep it up on the YouTube. And we're also going to bundle all the questions and write an article about it that will be published on the Utrecht University website. On Monday, the 20th of February, Utrecht University is also organizing a group meeting for those who, the students and staff who are affected by the earthquakes in Turkey. You can come together and talk about what happened, how it affected you, and how you're dealing with it. You can find more information about that group meeting in the description below. And there we will also include a link to Giro 555. Again, thank you very much, Rob. Thank you for watching. And our thoughts are with those who are affected.